Finding the zeros of polynomial functions. The rational zero theorem helps us to narrow down the list of possible rational zeros for a polynomial function. Once we have done this, we can use synthetic division repeatedly to determine all of the zeros of a polynomial function. Given a polynomial function f, we're going to use synthetic division to find its zeros. Number one, we're going to use the rational zero theorem to list all possible rational zeros of the function. Number two, we're going to use synthetic division to evaluate a given possible zero by synthetically dividing the candidate into the polynomial. If the remainder is zero, then the candidate is zero. If the remainder is not zero, then you discard the candidate. Number three, you repeat step 2 using the quotient found with synthetic division. If possible, continue until the quotient is a quadratic. Number 4, find the zeros of a quadratic function. Two possible methods for solving quadratics are factoring and using the quadratic formula. Example 5, we want to find the zeros of a polynomial function with repeated real zeros. We want to find the zeros of f of x, which is equal to 4x cubed minus 3x minus 1. The first step we want to do is the rational zero theorem, which tells us that if p over q is a zero of the function, then p is a factor of negative 1, which is the constant term, and q is a factor of 4, which is the leading coefficient. So, the factor of the constant term is negative 1, the factor of leading coefficient is 4. So we have plus or minus 1 in the numerator, and the denominator, the factors of 4 are plus or minus 1, plus or minus 2, and plus or minus 4. So if we divide the numerator divided by each denominator, we end up with plus or minus 1, plus or minus 1/2, and plus or minus 1/4. So, if we list all the possible rational zeros from this list, we get negative 1, 1, negative 1/2, 1/2, negative 1/4, and then positive 1/4. So, if we try the first rational zero, which is negative 1, let's go ahead and use synthetic division. So we're going to divide negative 1 into the function. Now keep in mind here that we also have a missing term. So we have a 0 for the x squared term. So we should get 4, 0, negative 3, negative 1 as our coefficients. We bring down the 4. Negative 1 times 4 is negative 4. 0 plus negative 4 is negative 4. Negative 1 times negative 4 gives us positive 4. And 4 minus 3 gives us positive 1. Negative 1 times negative 1 is negative 1. And negative 1 times negative 1, negative 1 plus negative 1 gives us 2. And so the remainder is 2. And so therefore we cannot use negative 1 because it is not a zero or a factor of that polynomial. Now let's try positive 1. We try positive 1 and we repeat the synthetic division. We're going to bring down the 4. 1 times 4 is 4. 0 plus 4 is 4. 1 times 4 is 4. 4 minus 3 is 1. And 1 plus 1 is 1. And negative 1 plus 1 gives us 0. So here we have a remainder of 0. So now that we have a remainder of 0, then we can rewrite the quotient now as 4x squared plus 4x plus 1. Now, since we know that 1 means that we have a factor of x minus 1, because that gave us a remainder of 0, so we know 1 is the 0 of the function, and then we know that this was our quotient, so we have x minus 1 times 4x squared plus 4x plus 1. Now we need to look at the quotient. Okay, and if we can factor this by any of the methods that we've used before, whether it is a perfect square trinomial. Now, if it cannot be factored, then you're going to have to use the quadratic formula. But in this scenario, we can factor it because it's a perfect square. So x minus 1 times, this becomes 2x plus 1 times 2x plus 1, which is the same thing as x minus 1 times 2x plus 1 squared. Now, we already know that 1 is a 0 because x minus 1 equals 0 gives us x equals 1. And the other 0 will have a multiplicity of 2 because the factor is squared. So to find the other 0, we can set that factor equal to 0. So we're going to set 2x plus 1 equal to 0. We subtract 1 and divide by 2, so the other 0 is going to be negative 1/2. So the zeros of the function are 1 and negative 1/2 with a multiplicity of 2. Now let's look at this graph of the function in figure 1. Notice that at x equals negative 0.5 here, the graph bounces off the x-axis, indicating the even multiplicity for the 0 at negative 0.5. And at x equals 1, the graph crosses the x-axis, indicating the odd multiplicity for the 0 of x equals 1.